Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using 9. This chapter begins our work with discrete variables, and in this chapter we're going to be talking about binomial probability distribution. So before we begin, to understand binomial distributions and probabilities, it's going to help to understand the binomial experiments and some associated notation that we're going to see with them. So let's cover that first. In a binomial experiment, it's going to have the following properties. First off, it's a fixed number of repeated trials, and that each trial can have only two outcomes, success or failure, on, off, true, false, doesn't matter, but two outcomes. And the probability of success with any trial is going to be denoted by p, and it's always the same. So like flipping a coin, what's the chance of it being heads? The probability is always the same for every trial. And that the trials are independent, that is, the outcome of one doesn't affect the other. So the coin flipping is a great example of a binomial experiment. So let's look at that coin flipping experiment. It consists of repeated trials. We flip a coin, in this case 2 times. Each trial can result in just 2 possible outcomes, heads or tails. The probability of success is constant at 0.5 every trial. And the trials are independent. The outcome of getting heads on the first flip doesn't impact the outcome of getting heads on another. So the most common notations we're going to see here is x is the number of successes that result from the experiment, and n is the number of trials in the experiment. P is the probability of success on an individual trial. Q is the probability of failure, which is just p it's 1 minus p. Now n factorial is the factorial of all the n's, and the binomial, the notation bx colon np, is the probability that an n trial experiment results in exactly x number of successes when the probability of success on an individual trial is p. And finally, NCR, using the factorial, is the number of combinations of n things taken r at a time. A combination is a selection of either all or part of a set of objects without regard to the order in which the objects are selected. The easy example I can give you is, assume we have 3 letters, A, B, and C. And we might ask, how many ways can we select 2 letters? Each possible selection would be an example of a combination. So the list could be AB, AC, and BC. Now the number of combinations of n objects taken r at a time is going to be, I can look at this 2 ways. Either the sum of the factorials, n times n minus 1 times n minus 2 all the way down to n minus r plus 1 divided by r factorial. Or, put another way, it could be computed as n factorial divided by r factorial times n minus r factorial. It's how you look at things like lotteries and see such incredible numbers, is when you look at the factorials are what adds so many unique possible combinations. So examples, I roll a dice 5 times. How many combinations of 2 numbers will there be? I can roll a 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 2, 2, 3, 2, 4. Again, the order isn't relevant, so we don't go back to 2, 1 again, because that was covered with 1, 2. So when I look at this, it's 5 factorial divided by 2 factorial times 5 minus 2. So 120 divided by 12 equals 10 possible combinations of numbers. So a binomial random variable is the number of successes x in n repeated trials of a binomial experiment. The probability distribution of a binomial random variable is going to be called the binomial distribution. So, suppose again we flip our coin 2 times and count the number of heads. The binomial distribution is going to look like what you see on the right, because I can have either 0 heads in those 2 flips, 1 or 2. My probability is 25% that I will get none, 25% that I'll get 2, and 50% that I'll get 1. So the binomial distribution has the following properties. The mean of the distribution is going to be equal to n times p. The variance is going to be equal to n times p times 1 minus p. And the standard deviation is the square root of the variance. The binomial probability refers to the probability that a binomial experiment results in exactly x number of successes. For example, in that table above, we saw in flipping a coin 2 times, the binomial probability of getting exactly 1 head in 2 coin flips is 50%. So here we're going to look, you can see this is the binomial formula. The probability of success on an individual trial is p, then the binomial probability is, again reading that formula, the probability based on the number of attempts and the probability within each attempt. It's a complex formula, and again, the neat thing here, folks, is remember, NIME is going to take care of all this for you. So this is really, right now, we're still leading up to an education to teach you so you understand the outputs of NIME. Suppose I cast a die 5 times. What is the probability of getting exactly 2 4s? Well, in this binomial experiment, the number of trials is going to be equal to 5. The number of successes is 2. And the probability success of a single trial is 1 in 6, or we'll say 0.167. Therefore, the binomial probability is 0.161. The cumulative binomial probability refers to the probability that the binomial random variable falls within a specific range. For example, is it greater than or equal to some stated lower limit or a stated upper limit? For example, we might be interested in the cumulative binomial probability of obtaining 45 or fewer heads in 100 tosses. This would be the sum of all these individual binomial probabilities. That completes this chapter of the class. Feel free to move on to the next chapter.